So, the first concept that we have got to discuss is the elementary concepts of magnetic circuits. So, we have all seen the magnetic properties of materials that is observed in nature. We have seen a bar magnet, we have seen how it shows its attracting and directive properties. We have seen a lot of things regarding magnets, and we know quite a lot of things about magnetism. So, what is the thing of our interest is how magnetic field is produced using currents. So, this revolutionary concept of the ability to produce a magnetic field by using a current, it has just done wonders. That is the basic principle of working of a lot of electrical equipments and machines, of the generator, of the transformer. Everything uses magnetism as its main principle. We also know that if a coil of wire is wound on a soft iron piece and if current is passed through the coil, an electromagnetic field is produced and it can act as a magnet, it can attract objects. We know all those things. So before we step into magnetic circuits, we have got to learn a lot of new things about magnetic circuits. So the first concept is, what is magnetic flux? Almost all of us will be familiar with what is magnetic flux. It is the number of magnetic lines of force that passes through an area. This magnetic flux is analogous to current in electrical circuits. But unlike current, this magnetic flux is not flowing, or it does not stop when there is a breaking in the circuit. There is nothing of that sort. But for easy understanding, we can consider magnetic flux as analogous to current of electrical circuits. And the next concept is the magnetomotive force. What is EMF, electromotive force? It is nothing but the driving force which drives current in a circuit. In other words, we know current is all about the flow of charges, but charges cannot flow on its own. There should be a force which drives this electrons into motion, and this is what is called EMF. And analogous to that, in magnetic circuits, we have MMF, or the magnetomotive force, which is a driving force for the flow of magnetic flux. So, MMF is the force which establishes the magnetic flux in a magnetic circuit. So, just consider a simple magnetic circuit which can be formed by a coil of wire wound on a steel ring, such that the magnetic field lines are almost inside the ring. So, just consider a coil of wire of n turns wound on this steel ring, and the current is passing through the coil. As the current passes through the coil, it produces a magnetic field, a magnetic flux, and the steel ring provides an easy path for the lines of force or flux to spread. This forms a simple magnetic circuit. If the current of I amperes flows through a coil of n turns, the magnetomotive force, it is the product of I and n, and its unit is ampere turns, AT. This is what is magnetomotive force. The next concept is magnetic field intensity. So, magnetic field intensity or magnetic field strength, it has close connection with magnetomotive force, MMF per unit length. That is what is magnetic field intensity. If the magnetic circuit or path in which the magnetic field is established is of uniform cross-sectional area, then the magnetomotive force per unit length is called the magnetic field strength or intensity, and it is represented by H. Note that I've said that if the magnetic circuit or path in which the magnetic field is established is of uniform cross-sectional area. This is very important. If we have a magnetic path which has non-uniform area, we just cannot divide the MMF by the total length. We'll have to divide it into sections and find the strength of all these sections and then add them up. This has got the unit of ampere turns per meter. And from the formula it's very clear. MMF has the unit of ampere turns and per length is ampere turns per meter. The next concept is magnetic flux density. So magnetic flux density is the amount of magnetic flux that passes normally through an area. Just consider a 1 into 1 piece of square area, and if there is a magnet in its close proximity, the number of electric lines of magnetic lines of force that passes normally through this area is called the magnetic field density. This has got a unit of Tesla and it is represented by the letter B. Its magnitude and direction, everything is given by the Biot-Savart law, which is very familiar to us. We have learned it in earlier classes. So now we have covered magnetic flux, which is analogous to current, and MMF, which is analogous to EMF. So one thing is missing, that is resistance. In magnetic circuits, there is something analogous to resistance in magnetic circuits, and that is reluctance. So like how resistance is the opposition offered to electric current flow, magnetic resistance or reluctance is the opposition offered to magnetic flux in a magnetic circuit. Like how Ohm's law gives a ratio of V by I as R, reluctance is the ratio of magnetic potential difference MMF and its corresponding flux. It's represented by S usually, and its unit is Henry inverse or ampere turns per Weber. Unlike resistance, we know when current passes through a resistive element, there is dissipation of heat and corresponding losses. But there is nothing of that sort. There is no heating up or that sort of things in reluctance. The inverse of resistance is conductance. And similarly, the inverse of reluctance is permeance. Now, like the relation R equal to rho L by A, we have a similar relation for reluctance also. But before we go on to it, we should know what is permeability. If we divide the flux density B by the magnetomotive force F, then we get the permeability of free space, which is a constant in air or free space. And its value is 4 pi into 10 raised to minus 7. It is represented by mu 0 and its unit is Henry per meter. A coil wound on a non-magnetic material or with just air or vacuum inside is called an air cord coil. And the flux density produced in such a core is very small. However, if the coil is wound on a steel core, the flux and its density are greater. We thus use a magnetic core to increase the flux density. And the ratio of the flux density produced in a core material to the flux density produced in free space or vacuum or a non-magnetic core is called the relative permeability, and it is denoted by mu r. Value of mu r is 1 for air or free space, and its value differs for different materials. So we thus come to the relation that B is equal to mu 0 mu r into H. And using this equation and the equation that phi is equal to B into A and F is equal to H into L, using these three relations, we can come to the relation of reluctance S. That is, S is equal to L by mu 0 mu r into A. This is a very significant equation, and that is the equation which we usually use to find the reluctance S. Now it's always beneficial if we always compare electrical and magnetic circuits. I already told you that EMF and MMF is analogous to EMF, then flux is analogous to current, reluctance is analogous to resistance, and there are a lot of relations between the two. So this comparison will make things easier to remember. It is R equal to rho L by A in resistance in electrical circuit, and L by mu 0 mu R into A is equal to S is the relation in magnetic circuits. Then conductance is the inverse of resistance, whereas permeance is the inverse of reluctance. Then there is no leakage of current. If there is a break in a circuit, the current flow ends there, or the circuit is broken and there is no flow of current. So leakage of current, that concept does not exist, but there can be leakage of flux. Leakage of flux through a air gap is possible. Similarly, there is a possible insulation of a material from electric field. That's possible. We can we can cover the substance by a conducting material, and we can ground it, and hence we can stop any sort of electrical interference, but no possible magnetic insulation is there. Magnetic insulation of a material is impossible. We cannot completely block the entry of magnetic lines or magnetic flux through a material. It's not possible. The next fact is current flow is caused by the flow of electrons. There is a physical flow of something. But in magnetic circuits, magnetic flux flow is misleading. There is no actual magnetic flux flow, it is just an effect. Everything related to magnetism is an effect. There is no physical way we can talk about it. These are the relation between electrical and magnetic circuits. Now, when we learn about magnetic circuits, one very important thing that we have to look into is series and parallel magnetic circuits. When we learned about resistance also, while we were solving problems on resistance also, we learned about series and parallel circuits. So, in electrical circuits, the parameter which we looked into was current. Here it's flux. What was series electrical circuit was, if a same current passes through two elements, then it is said to be connected in series. If two elements get the same voltage, or if different current splits when it reaches a point, and the principle of same current flowing through two elements cannot be applied, then it is said to be parallel. Here, analogous to current, we use magnetic flux to define what is series and parallel magnetic circuits. So first, when we look into series magnetic circuit, I would like to remind you about the formula which we learnt for reluctance, and it was L by mu 0 mu r into A. Keep it in mind. And for learning this, I would like to ask you to just think about a bangle. You know, the normal bangle which girls wear. And just think that this bangle is divided into 4 sections, maybe 4 colors. A single bangle is made of 4 colors. So now I'm saying that all these 4 different parts have different reluctances. How can these 4 parts have different reluctances? It can happen because, L by mu 0 mu r into A, right? So maybe it has different length, different area of cross section, and it can also happen because the material is different. So these 4 parts are made of different material, or one is longer and the other is shorter, or one part is thick and the other part is not so thick as that. Nowadays bangle comes in in different kinds, right? So just think of something like that. So, series magnetic circuit looks something like this. Not like a bangle, but it is a closed thing in which flux can complete its flow through it. It can start from a point and it can reach the other end also. So, when we consider the path for the flux, it comes to different reluctances. That is, a different magnetic path it has to cross to complete its flow. That is what is series magnetic circuit is all about. Now, unlike electrical circuits where air cannot participate in the flow of electricity, here air gap can also act as a magnetic path if the air gap is of a very low dimension. I mean, it is just for 3 millimeters, 4 millimeters, etc. Magnetic path can also be made by air gaps. So, if we consider a magnetic path which has different dimensions or different materials which give different reluctances to each part, we can consider it to be a series magnetic circuit. Now, see, very much like electrical circuits, the formula for total reluctance in series magnetic circuit is the sum of all the individual reluctances. Now, when it comes to parallel magnetic circuits, it is the same as electrical circuits. The flux splits into different branches depending on the reluctance. So, more flux passes into the area with smaller reluctance, and less flux goes into the part with more reluctance. Now, there are many parallel paths for the flux to choose from, which one to go through. In that sort of a case, we say that it is parallel magnetic circuit. Here, the total flux is the sum of the individual fluxes, and the total reluctance formula is same as that of electrical circuits, that is 1 by S is equal to 1 by S1 plus 1 by S2 plus 1 by S3 plus etc. The next topic is the principle of electromagnetic induction. The basic principle of electromagnetic induction was first discovered and formulated by Michael Faraday, and he discovered it through his 3 experiments. We are very much familiar with using a bar magnet and a coil with a galvanometer. When there was a relative motion between the magnet and the coil, the galvanometer showed a deflection. And his third experiment was using 2 coils, one coil fitted with a battery and a switch, and the other one a normal coil without any battery, but it contained a galvanometer. So, when the switch of the first coil was suddenly pressed on or off, there was a deflection in the second coil. It was from these 3 experiments that Faraday developed the law of electromagnetic induction, the first and second law of electromagnetic induction. The first law states that whenever the flux linked with a coil of wire changes, an electromotive force is induced in the coil. And the second law states that the magnitude of the induced EMF is proportional to the rate of change of magnetic flux. And if n is a number of turns and the change in flux is 5 Webers in a time t, then the induced EMF E is equal to n into d phi by dt. After these 2 laws were formulated by Michael Faraday, another rule regarding the direction of the induced EMF was formulated by Heinrich Lenz, and it's called the Lenz's law. It states that the direction of the induced EMF is always such that it tends to set up a current opposing the motion of the change of flux responsible for inducing the EMF. That is, the direction of the induced EMF always opposes change producing it. So these three laws are the basic laws that govern the process of electromagnetic induction, and these three laws have got application in all areas of electrical engineering, in the working of transformers, in the working of generators, everywhere. So let's look into the first problem on electromagnetic induction. It reads something like this: find the induced EMF in a conductor when rotated in a uniform field of magnetic flux 2 milliweber in 0.02 seconds. Given number of turns of the conductor is 100. Okay, so here we have to find the induced EMF. We have to find what is E. And the number of turns is given to be 100. What all are the informations that we have? The change in magnetic flux is 2 milliweber, and time taken for this change is 0.02 seconds. So we know induced EMF E is equal to minus N d phi by dt. For the time being, let us take the delta form of d phi by dt, that is minus N delta phi by delta t. So E is equal to minus N delta phi by delta t. We know the value of delta phi, that is change in magnetic flux, that is 2 milliweber, and the change in time is 0.02 seconds. Substituting all those in the equation, we get minus 10 volt. Now when it comes to the second problem, it is a current of 5 ampere when flowing through a coil of 1000 turns produces a flux of 0.3 milliweber. Determine the inductance of the coil. Okay, the current is given to be 5 ampere and the number of turns is given to be 1000. And the flux is also given 0.3 milliweber. Now we have to find the inductance of the coil. So we know what is the equation for self-inductance, L equal to N phi by I. We have learned it to be N d phi by di. So let's keep away all the differentials and let's take the magnitude, and L is equal to N phi by I is the formula. So all the values are given. When we substitute all those, we get the inductance to be 0.06 Henry. So the next concept is the concept of statically and dynamically induced EMF. In Faraday's third experiment, in which there were two coils, one with a battery and other with the galvanometer, we know there was no relative motion between the two coils. The EMF was induced due to the change in magnetic flux of the first coil, that is the sudden switching on and off of the first coil. The induced EMF is due to the change in the flux linkage due to changes in the circuit that produces the flux. This is thus a statically induced EMF, as there is no motion involved. Transformers work on this principle. Here E is minus N into d phi by dt. Now an alternative way to induce an EMF is to have a relative motion between the magnetic flux and the conductor, as in Faraday's first and second laws. A conductor or coil is moved relative to the magnetic flux. The magnetic flux or the field may remain stationary, whereas the conductor or coil moves relative to the flux or vice versa. In either case, the result is an induced EMF in the conductor. This EMF is thus dynamically induced one, as there is a relative motion involved. This is how voltages are induced in generators of electricity. If a conductor of length L is placed in a magnetic field of flux density B and it moves with a velocity v at angle theta with the magnetic field, then E is equal to BLV sin theta in dynamically induced EMF. In magnetism, inductance is the tendency of an electrical conductor to oppose a change in the electric current flowing through it. What is self and mutual inductance? Self-inductance is defined as the induction of a voltage in a current carrying wire when the current in the wire itself is changing. That is, the magnetic field created by a changing current in the circuit itself induces a voltage in the same circuit. This is self-inductance. The name itself suggests self-induced, that is, induced in the same coil. Here, E is equal to minus L into di by dt, where L is called the coefficient of self-induction or simply self-inductance. From this equation, it is clear that self-inductance is the voltage induced in the coil when there is a unit current change per second, and the direction of this induced EMF is opposing the cause producing it. Now we have two equations. E is equal to minus N d phi by dt and E is equal to minus L di by dt. From these two equations, we get L is equal to N into d phi by di. Now mutual inductance. When two coils are wound such that there is a common magnetic path, an EMF is induced in the second coil also due to the change in current and consequent flux produced by the first coil. Let N1 be the number of turns on the first coil and N2 be the number of turns on the second coil. Then the induced EMF in the second coil due to changes in the flux produced by the first coil is said to be due to mutual induction, and this property is called mutual inductance. The EMF produced due to mutual inductance in the second coil, E is equal to minus M into di by dt, where M is called the coefficient of mutual induction or mutual inductance, which has the same unit as self-inductance, that is Henry. The formula for mutual inductance M, mu 0 mu R into N1 into N2 into A divided by L, where mu 0 is the permeability of free space, mu R is a relative permeability, N1 is the total number of turns in the first coil, N2 is the total number of turns in the second coil, A is the area of cross section of the coils, and L is the length of the coils. Now we have been using the term linking of magnetic flux. What does this signify? When two or more coils are wound on a magnetic core, the flux produced by current in one coil will be linking with the other coil. But all the flux produced by one coil will not link with the other coil. That's quite natural. If all the flux is confined to the magnetic core and there is no flux leakage, we say that there is no leakage. Whereas if a part of the flux finds a path other than that of the magnetic core, say air, there is some leakage. To find the fraction of flux produced by one coil that is linking with the other coil, we use a term called coupling coefficient. Using the relationship of L1, L2 and M, we can derive the equation for coupling coefficient as M is equal to K into root of L1 into L2, where M is mutual inductance of the two coils, L1 and L2 are the self inductances of the first and second coil respectively, and K is called the coupling coefficient. The coupling coefficient is a term used to indicate how well the two coils are linking with the flux produced by either of them. If the leakage is zero, with all the flux produced by one coil linking with the other, the coupling coefficient will be unity. In such a case, the coils are supposed to be tightly coupled. If there is considerable leakage, as in the case of coils wound on a non-magnetic core or air as a core, the coupling coefficient will be much less than unity. Then these coils are said to be lightly or loosely coupled. The next most important concept is the concept of alternating currents. We all know that the earliest form of electricity that was put to use was direct current. But these days, the current which is used in industrial applications and domestic applications belong to alternating currents. Now, what is the difference between AC and DC? That is a very big question. To be very precise, in a direct current electrical system, the voltages and currents remain at a constant magnitude without change in direction. For DC voltage, a graph showing the voltage on y-axis and time along x-axis will appear as a straight line parallel to the x-axis. However, alternating voltages and currents change its magnitude and direction from time to time. Their graphs are called waveforms of the voltage or current. Variations can follow different patterns like square wave, triangular wave, or sine wave. Sine wave is the most widely used waveform due to a lot of its advantages. Now, why is alternating current put to a lot of applications these days? The reason for this is obviously that the ease by which electric power transmission and distribution is carried out at different voltage levels by the use of transformers with minimum power loss, even if the energy is generated at very remote locations far away from the load. Okay, now I told you that the most widely used waveform of alternating current is a sine waveform. The instantaneous value, that is the value at any instant, because it has continuous variations, the value changes at every instant. The instantaneous value at any instant is given by V is equal to Vm sine omega t, where Vm is the peak value of voltage in the sine waveform and omega is the angular rotation or angular velocity. T is the time at which instant we are taking the value. The current I is given by Im sine omega t, where Im is the peak value of current and omega is the angular velocity and t is the time. There can be a phase difference phi between voltage and current depending on the load. Now, while measuring the different parameters of the sine waveform, two important measurement parameters is the average value and the RMS value. Just visualize the waveform of the sine wave. It has two lobes, one above the time axis and one below the time axis, which is symmetrical. So, if we consider the average value for one complete cycle, that is from 0 it goes to the top, then it's come back to 0, then goes to the negative side, then come back to 0. This full cycle, if we are going to take the average value, that is the complete, if we sum up the whole of this area, we get 0, because for every positive value there is a corresponding negative value in the other half. So the total is 0. So we can find the average value for a half cycle. This is possible. For that we have formulas. The formula is V average is equal to 1 by pi into integral 0 to pi Vm sine theta d theta, where theta is omega t and the 1 by pi outside the integral and the limit 0 to pi corresponds to the length of the interval. Doing this integration, we get V average is equal to 0.637 Vm. That means the positive cycle has an average of 0.637 times of the peak, the Vm value. Since the average value does not exist for a complete half cycle, we go for RMS value. RMS, that is root mean square value. This actually goes with squaring each instantaneous value, then adding them and taking its root. That is what it actually means, but it is not easy to do it. So we have a similar integration process, and doing that process we get V RMS is equal to 0.707 times of Vm, that is 1 by root 2 times of Vm, and V RMS is 1.11 times V average. Now let us look into some important terms regarding alternating currents. To completely describe an AC waveform, we need some terms. We have to understand these terms really well to describe a waveform. So the first one is waveform. The variation of the quantity such as voltage or current or any other with magnitude on the y-axis against the variation of the angle, that is theta equal to omega t, on the x-axis is called the waveform. So if current is plotted against omega t, then it's current waveform. If it's voltage waveform. A cycle. Now the waveform repeats itself after every 360 degree, that is 2 pi radians. Then one cycle of the waveform starts at 0 and then it ends at 360 degree. So this is that cycle. Next very important parameter is the frequency and time period. So we visualize a waveform, and this sine wave, it keeps repeating in a particular interval of time, and the number of cycles it completes in 1 second. This is called the frequency of the wave, and its unit is Hertz, named after the scientist Heinrich Rudolf Hertz. And normally the frequency of the waveform that is available in India is 50 Hertz. Then that means it completes 50 cycles in 1 second. Then time period is the time required to complete one cycle. So if a cycle completes in 1 second, then the time period is 1 second. I told you frequency and time period is very much related. Frequency is 1 by time period and time period is 1 by frequency. So I told you in India the frequency of the waveform is 50 Hertz. So the period has to be 1 by 50, that is 20 milliseconds. Next very important term is the phase. The cycle is considered to start from 0 and completes its 1 revolution at 2 pi. It's not always necessary that it starts at 0 and it ends as 2 pi. But for convenience, we always take that wherever it starts, it's taken to be 0. Consider two waveforms as we are considering two waveforms simultaneously. So one has already started, its starting point is taken to be 0 and its ending point is taken to be 2 pi. Another simultaneous waveform is taken, and it's not necessary that it starts from the same point as the other waveform, but both have the same angular frequency, that is omega, that is the same, both have the same frequency, but both do not start from the same point. So there is a difference between the starting point of one waveform and the other. There is a difference. This is called the phase difference. The first one, which is taken as a reference, we think its waveform is Vm sine omega t. Then the other one is Vm sine omega t plus phi, where phi is the phase difference between both the waveforms. The next term is amplitude. We are very familiar with the term amplitude. Amplitude is a disturbance that of a wave from its mean position to the extreme position. So when it comes to a pendulum, if it is in the mean position, that is at the center, the maximum displacement that it gives to either sides, it is called the amplitude. In this case, the peak values, that is from the mean position, that is from the zero axis, it goes above and below. So these peak is called the amplitude of the wave, and it differs for different waves. These are the main terms that we have to remember while we are talking about alternating currents. The next question is how to find the RMS value of alternating currents. So we know RMS is root mean square value, and we'll have to take the square of each value, then add them and divide it by the total number and take the root of it. But this is a very tedious process, and when it comes to alternating currents, the value changes at every instant, and we can't take all the values and just add them up. This is not practically possible. So we have an integration formula to do this. To find this one, the first step is find the range, that is the time period where we have to integrate. So we know the time period is from 0 to 2 pi for for sine waveform. So the time period is 2 pi. Then we have the waveform formula as V equal to Vm sine omega t. Then the formula is V RMS is equal to root of 1 by 2 pi, that is the interval, root of 1 by 2 pi integral 0 to 2 pi Vm sine omega t the whole square d omega t. Simply if we are saying we have to take the root of 1 by interval, and then we are integrating in the interval the function square with the integrating with respect to that angular change, that is omega t. Here when we integrate Vm sine omega t the whole square with respect to d omega t, we get Vm by root 2 as a result. So we have to proceed with the same rules of integration as we have done in earlier classes in school. When we go by that way and take the root, we get Vm by root 2. So the RMS value of sinusoidal waveform, voltage or current waveform, is equal to 1 by root 2 times the peak value. Okay. Then we have learnt about the average value and the RMS value. So the average value is 0.637 Vp, right? Vm, right? So when we have the average value, RMS value and the peak value, there are some factors which we can define using these values. The first one is the form factor. The form factor is nothing but the ratio of the RMS value to the average value. So here it will be RMS value is 0.707 Vm divided by 0.637 Vm. For a sine waveform, this form factor is 1.11. That is the standard value of form factor for sine waveform. This is a very important and very useful relationship as far as electrical is concerned. Then we have peak factor. Peak factor is the ratio of the maximum value to the RMS value. That is Vm by Vrms or Im by Irms. It depends on different waveforms, and standard value for sine value, which is 1.41. Okay. So form factor and peak factor is what we have learned, and peak factor is also called crest factor. These two are the same, peak factor and crest factor.